All right, this last section in last topic in section 5.3 discusses independent events. So two events, A and B, are independent if the occurrence of one event does not change the probability that the other event will happen. So intuitively, that's what it means. If you know one event happens, it doesn't change the likelihood of the other. Mathematically, if you can prove these things, then you have independence. Basically, this is saying that the probability of A is the same as the probability of A given B. In other words, it doesn't matter if B happens, it doesn't change the probability of A. Similarly, if A happens, it doesn't change the likelihood that B occurs. So whenever you prove independent events, you're going to either think about it intuitively, or you're going to, or I should say, when you determine if two events are independent, you can either think about it or prove it mathematically. You don't need to prove both of the statements above. You can just pick one or the other. You don't have to do both. So events are events A and B independent? So yes, they are independent, or no, they're not. So the random phenomenon is to flip a coin twice. Event A is the first flip is a heads, and event B is the second flip is a tails. So the question is, does knowing event A happened change the likelihood that the second flip is a tails? And I think you should be saying no. If the first flip is a head, that does not affect or influence the second flip being a tails. So are these independent? Yes, they are. Okay. I guess I could prove it mathematically. The probability that the second flip is a tails is 0.50. What's the probability the second flip is a tails given the first flip was a heads? Well, it's just still 0.500. You're not. No. Either way. Number 2. Draw 2 marbles from a bag without replacement. You have 4 black and 4 red in the bag. So A is the first marble is black, and B, the second marble, is red. So if we select without replacement, the question here is, does the probability that the second marble is red change if you know the first marble is black? And I think most of us would say yes. If the first marble is black, it kind of increases the probability that the second marble is a red. So this does influence this, so these are not independent. If we wanted to prove it, the question is, what's the probability of B, and what's the probability of B given A? I think the second one, most people will probably agree with. What's the probability the second marble is red given the first is a black? Well, if the first is a black, we still have 4 red in the jar. However, we only have a total of 7 left over. It's this one here that some kids sometimes get a little bit confused about. What's the probability the second marble is red? What's the probability the second marble is red given you know nothing about the first marble? Well, that's just going to be 4 out of 8. Kids are going to say, well, but you took a marble out, so it should only be out of 7. But the thing is you don't know what marble you took out. You don't know if it was red or if it was black. So it doesn't really matter that you took a marble out if you don't know anything about it. You're still picking a second marble from 8 unknown marbles. I don't know, it's kind of confusing, but because these are different, these are not independent. Random phenomenon. Draw 2 marbles from a bag without replacement. 4 black and 4 red. The first marble is black, the second marble is red. Wait a sec, isn't that exactly the same as the example I just did? I think this is a typo. I think it should have been with replacement. My bad. So if you draw 2 marbles from a bag with replacement, if the first marble is black and the second marble is red, now after you draw that first marble and observe that it's black, you put it back in the bag, mix them up again, and then you pick a second marble. Well, now the probability that the second marble is red is 4 out of 8. And given that you draw through that first marble, it's still a 4 out of 8 because you're putting the marble back in and you're remixing it. So yes, these are independent events. Okay? So with replacement or without replacement makes all the difference in the world for independent events. Random phenomenon. Select a single person at random from the John Cooper School. Event A is the person is a male. Event B is the person has long hair. So this is kind of an intuitive one, a conceptual one. Basically, what's the probability that a person at our school has long hair? I don't know. A lot of people have long hair. I'm going to say maybe, I don't know, 50%, 40%. Let's say 45%. Probably higher than that. Maybe 55%. Now, what's the probability that you select a person with long hair given that person was a male? So now if you take the females out of the equation and you're just drawing from the males, what's the probability that male has long hair? Well, I think guys are more likely to have shorter hair. So the probability that somebody has long hair given from you're selecting from males is probably going to be smaller. Maybe 15 or 20%. Now there's still guys with long hair, of course, but there's certainly not as many of them. So knowing that you're picking a male changes the likelihood that you're going to get someone with long hair. So these are not independent. You might have said, you might realize that back in first chapter, we would basically be talking about whether there's an association between gender and hair length. And if there's an association, then you don't have independence. Kind of the same question. Random phenomenon, select a single person from random at the John Cooper School. A is the person's a male and B is the person has an A in math. So, what percentage of people get an A in math? I don't know. I guess I know what percent my classes do, but let's say the probability somebody gets an A in math, let's just say it's maybe 25%. That might be kind of high, or I don't know, whatever. So what's the probability that someone has an A in class given that person is a male? Well, we got to be a little bit careful here. We don't want to show any gender discrimination here. The question is, do you think guys are going to increase the percentage of people that have an A in math, or are going to decrease? If you think guys are better at math than girls are, or vice versa, then you might say this changes. However, I most definitely do not think guys or girls are better at math. So I think the probability that you're going to have an A in math isn't affected by whether you're male or female. So I'm going to say yes, these are independent. Okay. I might be wrong. It could go one way or the other. Who knows? But you get the idea. All right. So next example: gender and finger length. Is there a relationship between gender and relative finger length? The two-way table shows the gender of each student and which finger was longer on their left hand, their index finger or their ring finger. Basically, and this is something we kind of look at in class, but if you kind of take a look at your left hand, now obviously your middle finger should be the longest, but if you take a look at the relative length of your pointer finger and your ring finger, which one of those is longer. And it's going to be different for different people. I don't know if it's a genetic thing or what, but here's some data from a sample of, or from a population, I should say, of 452 students. You could look at the numbers. Are the events male and has a longer ring finger independent? Justify your answer mathematically. So to prove something mathematically is independent, I need to look at the probability of that you're a female and compare that to the probability that you're a female given you have a longer ring finger. Or you could look at the probability that you have a longer ring finger and compare that to the probability that you have a longer ring finger given you're a female. You don't have to do both of these, you just have to do one. I'm going to do this one here because it kind of makes a little more sense to me. So what's the probability you have a longer ring finger? So the ring finger was longer in 234 people out of 452 people. Oh, my daughter's crying. Give me a second. Hold on. All right, sorry about that. So the probability that you have a longer ring finger is this, which is 2, 3, 4 over 2, 3, 4. Over 452. Which is 51.8. So now let's find the probability that you have a longer ring finger given that you're a female. So for only the females, and by the way, yes, you could use the formula if you wanted to, but it's easier just to look at the females. Out of the females, 82 have a longer ring finger out of 212. 82 divided by 212. 38.7. So the question is, are these the same? They are not, so these are not independent. This seems to indicate that if you are a female, you are less likely to have a longer ring finger, which means if you're a male, you probably have a greater chance of having a longer ring finger. Yeah, that's it. Try to get one more in here. Multiplication rule for independent events. If you recall, the multiplication rule for the probability of A and B was a probability that A happens times a probability that B happens given that A has occurred. Well, if A and B are independent events, then this, by definition, this is the same as this, by the definition of independence. So it kind of is like a special multiplication rule for independent events. It's really not needed. I would just remember this and always do that. Not another lefty. 14% of the U.S. population are left-handed. If you randomly select 5 people from the U.S. population, find the probability that all 5 are left-handed. All right, so what's the probability that we get a left-hander and a left-hander and a left-hander and a left-hander, and we got to get 5 of them, so one more. Well, the probability of the first person's left-hander is 14%. Now the question is, what's the probability that the second person's a left-hander? Does it matter that you've already selected one left-hander from the population? The question is, are these events independent? If you're saying yes, I think that's kind of what the question wants you to use, but technically, I mean, I don't know how many people there are in the U.S. Gosh, I really don't know. 800 million, maybe? I don't know. And then if you let's say 10, let's just say 100 million. But 14% of them are lefties, so 14% would be is that 1/4? I don't know, something like this, right? So that's the probability that the first person's left-handed. Now, if you take one lefty out, now you only have this many lefties out of this many total. And I think you can see that these are technically not independent, meaning if you take one lefty out of the population, it very, very slightly changes the probability that the next person's a lefty. However, we kind of call this like a pseudo-independence. Because we're taking such a small number from such a huge population, it really doesn't change the probabilities all that much. So we just kind of multiply by 0.14 5 times, or just take 0.14 to the 5th power. And that's a fairly close approximation. 0.000054. 0.000054. It's very unlikely that if you select 5 people from the population of the US that you'd get 5 lefties in a row. Okay?